Welcome to Ask and Learn.
Here we have a position equation, and for part A we want to find the velocity, and remember that the velocity is the derivative of position. So we're going to use the chain rule, and we know that the derivative of sine is cosine, and then we have cosine of the inside, and then we multiply that by the derivative of the inside. And then we simplify just by writing the pi over 2 in front of the cosine. And so then for part B, we want to find v of 1, so we're going to substitute 1 into that function for t, and we have v of 1 equals pi over 2 times the cosine of pi over 2 times 1. Now the cosine of pi over 2 times 1 would be the cosine of pi over 2, and the cosine of pi over 2 is 0, so we have pi over 2 times 0, which is 0, and the units would be feet per second. For part C, we want to know when the particle is at rest. And a particle is at rest if its velocity is equal to 0. So we take the velocity, we set it equal to 0, and we solve for t. So we'll divide both sides by pi over 2. Now we have cosine of pi over 2t equals 0. And then we'll take the inverse cosine of both sides. So pi over 2 times t is the inverse cosine of 0. And that means we're looking for the angle whose cosine is 0. And there are infinitely many of them. There's pi over 2, there's 3 pi over 2, there's 5 pi over 2, and so on. Now to solve for t, let's divide both sides by pi over 2, and we get t equals 1, 3, 5, etc. One way we can describe that in general is if we let t equal 1 plus 2 times n, where n is any integer, although we want the smallest t value to be 1, so we really don't want any integer. We want n to be greater than or equal to 0. So we can just say n is a positive integer. Okay, for part D, we want to know when the particle is moving in the positive direction. And it will be moving in the positive direction when its velocity is 0. Now in the previous part, we found all the times when the velocity is equal to 0. Now we want to know when the velocity is greater than 0. So what we're going to do is we're going to split the numbers into intervals, and we're going to make those splits at all the points where the velocity was equal to 0. So we're splitting it at 1, we're splitting it at 3, we're splitting it at 5, etc. So those are the splits for the intervals. Now we want to see what the velocity is doing on each interval. So let's pick a number in each interval and plug it into the velocity and see if we get a positive or a negative. So I chose 1/2, 2, 4, and 6 to be the numbers I substitute into those intervals. And I got a positive, and then I got a negative, and then I got a positive, and then I got a negative. So what that's telling me, when it's positive, it tells me that the particle is moving in the positive direction. And when it's negative, it tells me that the particle is moving in the negative direction. So now we know the particle is moving in the positive direction from time 0 to 1 second, from times 3 to 5 seconds, 7 to 9 seconds, and so on, going on toward infinity. Okay, part E asks us to find the total distance traveled. Well, here's the thing. If the particle moves in the positive direction for a while, and then the negative direction for a while, and then positive and then negative, we've got to split this up and figure out the distance it travels each time. Otherwise, the negative distance is going to cancel out the positive distance. So we need to find the distance the particle travels from time 0 to 1 when it's going in the positive direction, and then the distance it travels from time 1 to 3 when it's going in the negative direction, and then from time 3 to 5 when it's going back in the positive direction, and then from time 5 to 6 when it's going back in the negative direction. And in order to do that, we're going to need a whole bunch of positions, and we get those positions from our original equation f of x. So we're going to need to know the position for each and every one of these endpoints of the intervals 0, 1, 3, 5, and 6. And a really convenient way to find those numbers without having to do all the calculating yourself is to grab your calculator. You know you're going to be graphing the function anyway when it comes to part H, so you can type the function into your calculator. Here I have y1 is my original function, and I've already typed y2 and y3, the derivative and the acceleration. We'll get to those later. So once you have your original function typed into your calculator, you can go to the table, And just check your table set real quick. Go to second window and check your table set and make sure you have independent ask, because that's going to allow you to type in your own x values. So once you have that set, go into the table menu and you can type whatever x value you want. You can ignore the ones I already have in here from last time, and you can type x equals 1/2, and notice the y value is positive, well, you get an approximate value there. You can type, which y values did I want? Let me go back. Okay, I didn't want 1/2. I wanted 0 and 1 and 3 and 5 and 6. Okay, so we go back to the calculator. We type 0. We get a y value of 0. We type 1. We get a y value of 1. We get 3 is -1. 5 is 1. And 6 is very close to 0, looks like. I'm going to call that a 0. All right, so now that we know that, to get the total distance traveled, we have to find the distance from time 0 to time 1, and that would be the position at time 1 minus the position at time 0. Take the absolute value, because when we're going in the negative direction, we're going to get a negative for this. And then to find the distance traveled from time 1 to time 3, position at time 3 minus position at time 1, etc., etc. Distance traveled from time 3 to time 5, position at time 5 minus position at time 3, and take the absolute value of each and every one of those before you add them all together. So we substitute our numbers in there, and then we get 1 plus 2 plus 2 plus 1. So that gives us a total distance traveled of 6 feet. For part F, we're going to draw the motion diagram. So we know that this particle is going to the right, to the left, to the right, to the left, or it's going in the positive direction, negative direction, positive direction, negative direction. So the motion diagram is going to capture that. So here we see the particle starting at time 0 at position 0. And then we see it's going to the right until we get to time 1. And then we see it's going to the left until we get to time 3. And it's going to the right until we get to time 5, and then it's going to the left. Now, it didn't say where to stop the motion diagram. It didn't say to stop it at time 6. So if you kept going, you would just have it going back and forth, back and forth, back and forth. Part G, acceleration. Remember, acceleration is the derivative of velocity. So we go back to our velocity function, and we take its derivative, again, using the chain rule. We have a constant. And then we had the derivative of cosine was negative sine of the function times the derivative of the inside. And we can simplify that, and we get the acceleration is negative pi squared over 4 times the sine of pi over 2 times t. Next, we want the acceleration at time 1, so we substitute a 1 in there. And when you're finding the sine of pi over 2 times 1, that will just be the sine of pi over 2, and that is 1. So we have negative pi squared over 4 feet per second squared. For part H, we want to use the graphing calculator and graph the position, the velocity, and the acceleration. So you saw already that I had those all typed in. And you also want to think about the numbers that make sense for this problem and choose a good viewing window. So we already saw some y-coordinates that were numbers such as 1 and -1 and 0, and we saw some x-coordinates which were numbers that went up, say 0 through 6 and beyond. So for my window, I decided to try going from 0 to 10 on the x-axis and from -3 to 3 on the y-axis. And you can always modify those if you don't like what you're seeing. So now we press graph, and what we see is the blue one is the original position equation, the red one is the velocity equation, and the black one is the acceleration equation. Finally, we're going to find out when the particle is speeding up and when it's slowing down. It will be speeding up when the velocity and the acceleration are either both positive or both negative, and it will be slowing down when they have different signs. One of them's positive and one of them's negative. So we already figured out where the velocity was positive and negative, but we need to know where the acceleration is positive and negative. So first we start by finding where the acceleration is equal to 0. So we take our acceleration function and set it equal to 0. Divide both sides by negative pi squared over 4, and we're left with sine of pi over 2 times t equals 0. we can take the inverse sine of that. So what we're looking for would be the angles that have a sine value of 0. And the angles that have a sine value of 0 would be 0, pi, 2 pi, 3 pi, 4 pi, all the multiples of pi. Now to get t by itself, we divide both sides of that by pi over 2, and we end up with t equals 0, 2, 4, 6, 8, etc. All the evens. So we could say that t is 2n, and in this case, the smallest n can be is 0, so we'll say n is a whole number. N is 0, 1, 2, 3, etc. Okay, so now what we want to do is break up our number line into intervals. We have to break it at 1 and at 3 and at 5 and at 7 and at 9 because those were the places where the velocity changed sign. But we also have to break it up at 2 and at 4 and at 6 and so on because those are the places where the acceleration is changing sign. So what we want to do then is analyze the sign of the velocity and the sign of the acceleration on each of those intervals and determine if we have the same sign for speeding up or opposite signs for slowing down. And this is another great place to use your calculator. If you go back to the table, and my y2 column will be my velocities, and my y3 column will be my accelerations. And what I could do is just take numbers from each interval and type them in, and I'll be able to find out whether the velocity is positive or negative and whether the acceleration is positive or negative. So I did that, and I have all the signs here. So based on that, we know that it's slowing down when the signs are different. So it's slowing down from time 0 to time 1, from time 2 to time 3, from time 4 to time 5, and so on and so on and so on. And it's speeding up when the signs are the same. So it's speeding up from time 1 to time 2, from time 3 to time 4, from time 5 to time 6, etc. So if you're looking for an algebraic way to express that, we can say that it's slowing down from time 2n to time 2n plus 1, where n is a whole number, not an integer, and it's speeding up from time 2n plus 1 to time 2n plus 2.